Thank you for your introducing me. I can start now. I'm ready. Can I start?
Yes, please go ahead. Please go ahead.
Okay. Now this presentation is about the performance evaluation of reverse osmosis pre-treatment technology of brackish groundwater. The contents of this presentation is the introduction, the previous studies and experimental setup, case study objectives and experimental results, ROSA software, comparison of experimental results against ROSA results, and conclusion and references at the end. First, our introduction. Desalination of brackish groundwater in Egypt, as you know, had great potential with respect to the availability of the resources. All major aquifer systems in Egypt contain huge quantities of brackish groundwater. The exploitation of this resource is still limited. With the current cheap price of brackish water desalination, there is growing interest towards its exploitation. Brackish water for reverse osmosis plants in Egypt confirms the potential of this solution. This paper presents a study of the effect of variation of different operating conditions on the performance of brackish groundwater reverse osmosis unit. This was achieved experimentally by using brackish water reverse osmosis desalination test rig, and there were samples of experimental output parameters were used and ROSA input parameter to check the accuracy of our experimental results, of course. And however, there were some deviations, but it doesn't exceed 10%. As you know, Egypt is located in the North Africa, bordered on its north coast by the Mediterranean Sea and on its eastern coast by Red Sea. The main source of water in Egypt is the River Nile. And of course, due to the rapid growth of population and the increasing consumption of water in agriculture, industry, domestic use, it's expected that Egypt will rely to some extent on groundwater to develop the new projects. Brackish groundwater desalination is one of Egypt's most potentially significant water resources. Most aquifer systems in Egypt contain high quantities of brackish groundwater. Here I am introducing our aquifers here in Egypt. The Nile Valley aquifer, first one, Nile Delta aquifer, and Moghra aquifer, and coastal aquifers, and Nubian sandstone aquifer. This all is from granular rocks type. And we have also the fissured hard rock aquifer and fissured and karstified aquifer, which is limestone rock type. The salinity of groundwater varies in Egypt between about 3,000 to 5,000 parts per million. Reverse osmosis is the finest level of filtration available. The reverse osmosis membrane acts as a barrier to all dissolved salts and inorganic molecules, as well as organic molecules. First, we'll have some talking about the previous studies in this about the reverse osmosis. The first one was Abrayan. He studied the effect of the feed water temperature and the feed water pressure and the feed water salinity on the performance on the small size brackish water reverse osmosis desalination. He found that the increase of feed water pressure or temperature results in a recovery ratio increase, while the increase of feed water salinity leads to a decrease in recovery ratio. The second study is Lilan de Safoy. They concluded that the temperature of the feed solution of the membrane desalination system had several effects, such as the temperature. Once temperature increases, the diffusivity of the solute also increases, and the desalination energy consumption decreases. As we see from the figure, here on temperature increases, okay, the diffusivity increases also. Our objective. The main study objective is to evaluate the performance of small-scale reverse osmosis unit. This will be done by several steps. First one, we'll make like a practical test rig. The second one, a theoretical performance estimation of reverse osmosis using the ROSA, which is the reverse osmosis system analysis software. After that, we will compare between our experimental study against theoretical performance. Last thing, we will make a regression analysis from the experimental results. The first experimental setup, we will make an experimental test rig includes about 150 experiments using brackish water. At first, it will be 6 different salinity from 1,000 to 6,000 parts per million. After that, we'll make it for 5 different temperatures from 15 to 35 centigrades. And the third thing will be for 5 different pressures from 12 to 28 bar. The saline solution is prepared by dissolving a certain amount of sodium chloride in tap water to obtain the desired total dissolved solids. As we see in our figure, the first is a feed water tank, and it is we can control the temperature using an electric heater. Okay. After that, the water will pass through a suction valve to feed water pump. This feed water pump is a low pressure centrifugal type. And after that, it will pass through 2 filters, cartridge filters, and through a pressure gauge to a high temperature pump of a piston type. It gives about 10 liters per minute to the membrane module. Okay, and after that, the output of the membrane modules will be 2 outputs. One through the throttle valve, which will be the brine water, the brine tank, and the second will be through the flow meter to the permeate tank or the permeate water. This is a picture of the reverse osmosis test rig in real. Okay. Our results here. I have several results. The first results, we found that increasing the feed water pressure, okay, increases also permeate flow rate. And increasing of the feed water total dissolved solids like this, okay, decreases the permeate flow rate. Second result, increasing of the total dissolved solids will increase the brine flow rate. Another result is decreasing of the feed water total dissolved solids will make the recovery ratio. The recovery ratio increases and permeate flow rate also increases. Another result, by increasing the membrane salt rejection, permeate total dissolved solids decreases. And when decreasing the total dissolved solids, permeate total dissolved solids also decreases. Another result, when increasing the permeate flow rate, okay, the specific energy consumption increases. Decreases. And with the increasing of the total dissolved solids, it increases the specific energy consumption. For results, the effect of changing feed water pressure and temperature at constant feed water flow, for example, 1 meter cube per hour, and at constant feed water total dissolved solids, which is 5,000 part per million. And by changing the feed water temperature from 15 to 35, 6 steps, and for the feed water pressure ranging from 12 bar to 28 bar, and by increasing the feed water pressure, this all will lead to increasing feed water pressure is to increase the permeate flow rate. Another result, increasing feed water temperature, okay, increases the permeate flow rate. And increasing the permeate flow rate, the brine flow will decreases, and increasing the feed water temperature will decrease the brine flow rate. Another result, by increasing the permeate flow rate, okay, the recovery ratio will increases, and by increasing the feed water temperature, recovery ratio also will increases. Another result, by increasing the membrane salt rejection, the permeate total dissolved solids decreases. And by decreasing the total dissolved solids for the feed water, it also decreases the permeate total dissolved solids. Another result, when increasing the permeate flow rate, the specific energy consumption decreases. And when increasing the water temperature, also the specific energy consumption decreases. Now, we will leave our experimental and comes to the reverse osmosis system analysis software. The reverse osmosis system analysis computer program, it calculates the feed pressure, the permeate quality, and the operating data of all individual elements. It's easy to optimize the system designed by changing the numbers and type of elements and their arrangement. When we use ROSA, first we must define our project information. After that, we must identify the feed water source and the feed water type and analysis, and our feed water treatment, pre-treatment, and filtration. As we see in the figure, first we enter the project name and date and description. After that, we identify the feed water type and the total dissolved solids and temperature. After that, we make for the system configuration for the membranes and flow rate and recovery ratio. After that, we get reports for all our results with, for example, the recovery ratio, something like that. And when we make a comparison between our experimental results and the ROSA results to know the quality of our experiments results, software ROSA was used for testing the accuracy. As I told you, experimental results where a sample case was taken, for example, a total dissolved solids, 6,000 parts per million, and the feed water flow rate and total dissolved solids and pressure were taken as inputs parameters in the, for ROSA software at feed water temperature about 25 centigrade. The output parameters will be the permeate flow rate, prime flow rate, and recovery ratio, permeate total dissolved solids, and the specific energy consumption. Will be, of course, this is a result from the ROSA. We're taken to make like a comparison, as I told you, with the experimental results. And for your knowledge, the deviation between them is not so far. It's only 10%. Doesn't exceed this ratio. We make a comparison for some cases here. When increasing the permeate flow rate, the average deviation between experimental, now as we see, the experimental is that green one, and the ROSA is the black one. The average deviation between the experimental permeate flow rate and ROSA at the lowest feed water pressure will be about 10%, and at the highest it's about 7%. Also, and decreasing in the prime flow rate, the average deviation between the experimental prime this green experimental prime flow and the ROSA prime flow rate at the lowest is about 12. Bar was doesn't exceed 3%, and at the highest doesn't exceed 8%. Another result, when increasing in recovery ratio, the average deviation between the experimental recovery ratio and the ROSA recovery ratio at the lowest feed water pressure is about 10%, and in the highest about 7%. Also, when we compare here the decrease of the total dissolved solids, the average deviation between the experimental permeate total dissolved solids and the ROSA permeate total dissolved solids at the lowest water pressure is about 32 parts per million, and at the highest it's about 25 parts per million. Also, and decreasing in the specific energy consumption, the average deviation between the experimental specific energy consumption and the ROSA specific energy consumption at the lowest feed water pressure, 12 bar, it will be about 10%, and at the highest pressure, it's about 6%. Our conclusion. The following conclusions are the effects of feed water pressure can be obtained for permeate water produced and brine rejected recovery ratio, permeate total dissolved solid, and specific power consumption at different feed water total dissolved solids feed water temperature. We have three conclusions. The first one, if we make the total, the constant feed the water total dissolved solid constant, and if we make the temperature the temperature also will be constant, and we when by increasing the feed water pressure, we will find the following. We will find that permeate flow rate and recovery ratio increased, while brine rejected and permeate total dissolved solids and specific power consumption decreased. In the second case, we will make the pressure and temperature constant, and we will increase the total dissolved solids. What we will see? We will see here that permeate flow rate and recovery ratio decrease, while the brine rejected permeate total dissolved solid and specific power consumption increase. The last case, we will make the pressure and the total dissolved solid will be constant, and we will increase the temperature, the water temperature. We will find what? We will find the permeate flow rate and permeate total dissolved solid and the recovery ratio increase, while the brine rejected specific power consumption decrease. This, of course, my reference, and thank you very much for listening my introduction.